Today we shall discuss an important topic which is pitting corrosion. Pitting corrosion of metals is it can cause a severe damage to the structural integrity, because the rate of corrosion in the pit can be very high. It can be about a million times higher corrosion rates as compared to the surrounding matrix. So, the pitting corrosion is very insidious. Can cause accelerated corrosion. The localized areas of a metallic component it can ultimately can lead to perforation. It can be a leak. Sometimes the pit can act as initiator for say stress corrosion cracking. It can be initiated for simple fatigue, or it can be even corrosion fatigue. You know the reason? Because when you have a pit which is very localized, it can be a stress riser. The stress intensity at that location can be quite high, and so the crack can initiate and grow even below the yield point of a metal. So, pit is in fact is very detrimental, can bring down the component life quite significantly, leading to premature failures. I just want to show some illustrations how this pit can really look like. I don't know how clear it is to you. It's a long shot and taken on facade. This is stainless steel. This is, you can see that there is a stainless steel here, right? You can see here is a stainless steel, and you see some fine dots appearing, right? And these fine dots are actually pits, and these pits appeared within about 6 months to 1 year of commissioning of this particular structure, because it was at the sea front, and the sea front, that you have a lot of chlorides being carried by the wind, and the chlorides deposit on this stainless steel structure, that leads to pitting corrosion. And this is a civil engineering structure, it's you would in the same location you would see here slightly better, I suppose. You can able to see a pit here, right? You can able to see a pit around here and a pit around here, and you see pits here, right? So, and of course you have tiny pits somewhere around here. You can see lots of tiny pits which are visible to the naked eye, okay. And again it is a 316 stainless steel. You could see the pitting happening within 6 months to 1 year, okay. They become very severe where they were welded. See that here, right? Right? I hope you were able to see this reddish brown spots, okay. These spots, they do correspond to severe pitting. Two kinds of problems here. One is the loss in the structural integrity, otherwise the cosmetic appearance of the stainless steels, right. You have reddish brown color, and especially you are talking about household appliances or the facades of a house, and which are all can cause kind of appearances which are not really acceptable. Now these are all macroscopic view of the pits, right, and if you see in the microscope sometimes these pits appear to start with the microscopic levels actually. You guys are all know, right, you have done already, earlier we have seen that what is polarization and how the polarization of passivating metals look like. When you analytically polarize, you get a passive region, and you rise the potential further, you get into pitting regions, okay. And if you look at the samples after the anodic polarization, and you will see a very microscopic pits here, okay. You see these pits are very microscopic in natures. Many of them are all hemispherical in natures, okay. That is how the pit starts actually, okay. In fact, the pit could start at the submicroscopic level actually. Submicroscopic means less than 1 micron actually can happen. So these are the kind of pits happened in the case of stainless steel, which is 304L stainless steels, and this stainless steel was plasma ion implantation technique, okay, where you implanted nitrogen in the stainless steel, and you can see here that it's untreated, right, and treated with the nitrogen, and you can see that the number of the depth of pit here is reduced as compared to over here. So in this case the nitrogen addition has improved, but of course the treatment was done at different temperatures. At a higher temperature you can see that the pits become more. Essentially this is a PhD work, okay, wherein they converted the surface so that it can have higher pitting resistance and higher passivation. In that case they have added nitrogen by plasma source ion implantation, or also called as plasma immersion ion implantation technique, okay. So essentially I want to show that these all can be microscopic, you can start with, it can be even submicroscopic levels. These pits start and then they grow, and they can start damaging. Sometimes the pit also can have a very complex morphologies, we will see later actually. You can see here these pits These are all corresponding to a stainless steel where nickel was substituted with the manganese, right. And why people substitute nickel with the manganese? Because the manganese is cheaper and also it can stabilize the austenitic phase. So it's an equivalent of a 304 stainless steel, but very low nickel content with more manganese content. You see here the pitting behavior is quite severe, you know. See compare these two now, you know, and you just see this. The left side corresponds to the manganese substituted one, actually you replace nickel with that, it's kind of nickel now. The one with nickel is certainly far better compared with the one replaced by manganese actually. As I told you, the pits can be very complex, you know, depending upon the microstructures, you know. So this is a slightly you know irregular morphology of the pit that you see here, okay, and this essentially is a composite, right. It's a A356 aluminum alloy actually, wherein you add silicon carbide particles added. This is essentially used for the rotor disc, you know, for the automobile applications, you know the brake disc actually, you know, is normally made up of cast irons, but cast irons are very high density, so they want to substitute with aluminum, but then aluminum suffers very high severe I would say wear problems. So what happens is they add it with silicon carbide. The silicon carbide gives you good reinforcement and so the wear resistance now. So you can see that the pits are more complex. It takes the contour of some of these silicon carbides. Okay, look at this shape of this. This follows the contour of the silicon carbide particles. So you can have a pit which can be irregular pit based on the microstructure of the material actually. That means the metallurgy also plays a very important role in pitting of the steels and other alloys. So what we like to say is that the pit can start at microscopic and submicroscopic level, then grow and then perforate. The structures. That is why they are quite deleterious. Look at this corrosion at the microscopic level, right. That means there is no significant change in the weight, change in the mass of the structures. So there is going to be no significant change in the mass of metallic structure. In pitting corrosion. So the test like mass loss test has no meaning, right. And why does it really originate pitting? There are a lot of studies, you know, there are probably hundreds of papers which are devoted to understand the pitting mechanism, pitting characteristics and so on, and I do not think we have now the last word in understanding the pitting mechanism so far. Of course, a significant progress has happened in understanding pitting corrosion, but still there are several steps of pitting we do not still understand. In this course, I am going to be a little brief because it is a first course and will not go into too much of science of the pitting corrosion. But however, if you are really interested to know more, I would recommend strongly this article by G.S. Frankel. This article is a review. And it is published in Journal of the Electrochemical Society. It is a very good review. Okay, it covers quite a bit of fundamentals of pitting corrosion. To start with, can pitting occur in all cases? In all corrosion system? The answer for that is it happens only in the passive system. In the passive metals. If the metals do not passivate, there would be no pitting. Passivation is an important criteria. First, the second, you need aggressive anions. You need aggressive anions. So even when the metal is passive, it may not pit unless there are specific aggressive anions. Okay. I give some examples. What are the metals you know of which are passivating in wide environment? Yeah, stainless steels. Yes. Yeah. Then aluminum. Titanium. And its alloys. There are so many other metals, right? You have, for example, you can have tantalum, zirconium, there are several metals which are passivating. It is also possible that you can passivate even pure iron under given pH conditions, right. We have seen the Purbe diagram. It is not necessary that the stainless steel can passivate in all cases, not necessarily, but predominantly yes, from the engineering point of view, these metals, they exhibit passivation. Now all of them they can undergo pitting, okay. For example, stainless steels pit in chloride media, so as aluminum. Titanium chlorides at ambient temperatures, no. At high temperatures, yes. But you can have like bromide, for example, can pit. So passivation is an important criteria for pitting to occur, okay. And predominantly these metals, they suffer pitting depending upon how severe the environment is, and what kind of, when I say environment, it means the temperatures, it means the nature of the anions that we think about, and both are included. As I told you, pitting corrosion is not so far well understood. Now if you take a, let us say, if you consider a polarization curve, if you know of this is very familiar to you, right, and this is the potential, we call them as E-pit, or also called as pitting potentials. Now if you look at the voltage here, let us say typically a 316 stainless steel in chloride medium, maybe the E-pit could be about plus 200 millivolts versus saturated calcium electrode, right, pitting potential in, let us say 3.5 8% NaCl solution. But actually if you look at the driving force for pitting, it is very enormous. Now what is this potential? This potential is with respect to the solution, right, the potential of the metal with respect to the solution as measured by a reference electrode, in this case a saturated calcium electrode. So I am measuring the potential of this metal in relation to the solution, so 200 millivolt. But if you look at the film thickness, when I say film thickness, I mean the passive film thickness, right, they are in the order of nanometers. The metal is highly conducting. This film you can consider as approximately you can say is insulating. Or you may consider as a semi-conducting, both, you know. So, it is a barrier for the flow of the current, is it not? When I apply a voltage, the current is not rising, the current remains steady state here. This is called a passive current density, right? This is your IP, passive current density. Because it is, the film is offering a barrier resistance. But if the film thickness is in nanometers and even you apply, let us say 0.2 volt, what is the field across the film? The field across the film turns out to be about 10 power 6 to 10 power 7 volt per centimeter. What is the field voltage by the distance over which the voltage is applied, right? Now look at this here. So it is a very high field. That means the metal is about to have an electrical breakdown, right? An electrical breakdown can happen, right? So it is in the threshold of the electrical breakdown. One aspect of it. The second aspect of it is the passive current density is of the order of what? It is of the order of 10 power minus 6 to 10 power minus 7 amperes centimeter square. But if you look at the active metal dissolution, at the bad surface, it is about 1 to 10 amperes per centimeter square. Do you understand this? Do you understand this concept? Okay. The passive current density at these locations, right, you measure it, they are all in terms of microamperes. If the film breaks and if you expose the bare metal, the current density over here is the order of amperes, 1 ampere to 10 amperes per centimeter square, right. So, how many times the metal corrodes here as compared to the corrosion of the metals in the passive state? How many times? It is about 10 power 6 is about 1,000,000 times corroding at higher rates. So, if you look at the film breakdown, if due to some reasons the dissolution at that location becomes very severe, the rate of corrosion can be of the order of 10 power 6, 10 power 5 depending upon to what extent the bare metal is exposed. So, pitting corrosion becomes very, very severe, very, very insidious, and it happens at the microscopic level. I hope I have conveyed the points clearly to you to understand here. Okay. So, this is a very important type of failure. That is why a lot of work has gone, a lot of research has gone to understand the pitting corrosion of metals. Now, let us look at the pitting. What it consists of? It consists of passive film breakdown, then we call it as metastable pitting, third we call them as a stable pitting. Let me explain to you what do I mean by these three events. Okay, these are the three events, simplified events of pitting corrosion. The passive film breakdown. Now let us take the case 1. Now what do you mean by a passive state? What do you mean by, so what is happening in a passive metal? You get a definite passive current density, there is a film formation, but even then there is a definite current flowing across the film. So there is a metal dissolution, it is not that there is no metal dissolution, the metal dissolves but dissolves at a lower rate. So the passivity is a dynamic process. Of film breakdown and passivation. It continuously happens, right? The only thing is the rate of repassivation or whatever, and you can call it repassivation. You use the term repassivation, may be more appropriate. Okay, so so if we can quickly heal, then the current comes down. Okay, now they are all happening at nano levels. I when I say nano, I talk about spatial, right? Nanoscopic levels. Spatially, they occur at the atomic and the nano levels. The metal atoms dissolve and there is repassivation are taking place. But what can happen is, if you raise the potential is increased, if the potential is increased, or if some aggressive anions are present, film breakdown dominates. You may call this as initiation. As I told you, the initiation process is still less understood. The film is getting damaged, the film is getting broken actually, okay. The bare metal is exposed. When it is exposed, then what happens? It leads to metastable pit. You know what do you mean by metastable? Anybody? It is between a stable and unstable state, right? A stable state and an unstable state, in between the state is called as a metastable state. It can either go to a stable state or it can move to a unstable state. That is called a metastable state. Okay. In the metastable period, what happens? The damage is quite visible. So what do you mean by that? If you normally observe the anodic polarization curves of, let us say, stainless steel, aluminum alloys, some cases even titanium alloys, you start from the E card, right, this is your E card, okay, and you rise the potential, you go to the critical current density, then passive state, current apparently looks very stable current, right. When you start increasing, the current starts fluctuating. And this is called as metastable place. Why I call a metastable here? The pits are visible. Pits are visible to a microscope. You just see them in the microscope. They can be 1 micron or half a micron visible, right? As opposed to the film breakdown, right? As opposed to film breakdown, that is initiation process, no visible change is seen. You do not see them anything, right. In other cases, you see that there is a dynamic process of metal dissolution and then repassivation taking place, and see them in the microscope, you would not see any features. But over here, you observe in the microscope, you see microscopic size pits appearing, disappearing, appearing and disappearing. That means what? It becomes truly metastable, and some of these pits may become stable later, right. So you see a metastable pit here, okay, which are observable in the microscope, and these metastable pits are microscopic in nature, okay. Some of them becoming stable pit, okay, and many of them repassivate. It goes to the original state of passivity. Now what does it mean? When you start moving from the corrosion potentials up towards the noble side, okay, noble side, you see the current start fluctuating, and then the current becomes here, you see here what happens, here the current is steadily increasing, and this becomes a stable pit. At this particular potential, it means a stable pit. So called E pit you describe is nothing but the pit that forms become stable, okay. The pit does not disappear above that particular potentials. At E pit and above, the chances of the pit remaining stable is very high. Below the E pit, the chances of pitting becoming stable becomes less. In fact, it becomes less as you start moving down from here, or so to say, it is possible to have a pit even at this particular place, over here, over here, over here. But what does really mean in real terms? The in real terms, the probability of the pit that is formed here becoming stable is so less compared to the probability of the pit so formed becoming stable. So this probability is quite large here as compared to this. That means the concept of E pit becoming a unique number is not correct. The pitting can occur below the pitting potential as well. At E pit and above, for sure the pitting will take place. Hope I am making the point clear to you. So the concept of saying that E pit corresponds to pit initiation is a little bit not a right terminology to use. All we can say is that yes, the pit will start stabilizing at that particular potentials. Okay, am I clear to you actually? Am I clear? Okay, so this is something very important to look at it. In fact, this has led to some concept of what is called as induction time. Actually, just to make some remarks, I would say pitting corrosion, pitting tendency I would say is a function of applied potentials, the chloride or anion concentration, then the time, which is going to be other factors. Okay, E, where here E is applied potential, chloride is the air concentration, of chloride or other anions, time is the time of exposure. Now, if you take for example, let us draw this diagram of polarization curve. Suppose like this, okay. Suppose you take these places, these points, suppose you take, and I hold the sample at that particular potential, time versus the current, log I you can call it, okay, log I current. If I hold at potential corresponding to the point D, the current increases D here. See what happens? This is your, let us say this is your IP, this current is, base current is IP here. Here what happens? The current will remain here, and then this is going to be C, this is going to be B, it's going to be A here. the increase in current corresponds to the pitting of the metal. This is given some gross schematic here, okay. Do not worry about the values, just look at the relative positions of these current versus time curves. So what does it mean? If you are going to hold it at D, the pit starts immediately, it does not take more time. If you hold it, if you reduce the potentials, it takes longer time, and so on B and so as A, right. So which means that the chances of metal pitting in an environment, it depends on what? It depends upon not only the potentials, also the time factors, okay. So this is something you should be looking at actually. So now the pit becomes stable, right. What makes a transition from metastable to stable pit? Here there is a lot of similarity between a crevice corrosion and a pitting corrosion here, okay. What makes the pit stable, right? The pit can repassivate, that means it can form the film, that means the pit becomes unstable, or the pit will continue to dissolve and grow, that means the pit becomes stable, right. So what makes this pit stable? Now there are several theories are there. We will make it very brief and somewhat simple. Let us take a surface. Let's take a surface. This is the passive film, okay. The cathodic reaction and the anodic reactions, they occur all through, right. The cathodic reaction may be considered as here you can have a cathodic reaction. Generally, for a stainless steel to passivate, the cathodic reaction has to be what? Has to be, if it is an acid, if you are going to use an acid, so cathodic reaction is generally the oxygen reduction reaction, that only makes the potential in the passive region, right. Otherwise it won't make the, it won't render the metal passive, you need to shift it to the passive region. So the cathodic the cathodic current, the cathodic reaction must have noble potential. So all through you have a metal dissolution and as well as the oxygen reduction reaction taking place like this. Now if there is going to be a pit formed, assume that there is a pit formed, if the pit is covered by corrosion products, passive film, whatever can happen, then it becomes an occluded cell. What is an occluded cell? The occluded cell, there is no convection, there is only diffusion process, right. So it is only a diffusion process here. No, in the pit, the so called metastable pit, assume that it is a metastable pit, okay, it's metastable pit. There is a pit formed here, it is covered with some corrosion product or something. The metal continues to dissolve below this cover, okay. Here the metal dissolves continuously, right. Okay, it dissolves continuously. It will generate various cations. For example, if you have a M go into solution as Mn plus an electron, this becomes an anode. Now the surrounding area becomes cathode, and over here oxygen content drops. Why does the oxygen content drops? Because it is covered with a corrosion product. Now you have these metal ions generated here, right, and these metal ions when they are generated, what happens now? You have now the generation of H plus ions. So this is also going to promote chloride ion migration. Chloride or maybe iodide or whatever, depending upon the anions present in the electrolyte, and they can migrate to this and can form hydrochloric acid. It is somewhat similar to crevice formation, am I right? Somewhat similar to crevice corrosion formation. Now the question is, when will the pit be stable? The pit will be stable if you form the acid, right. Pits become stable, pitting becomes stable if the pit is acidified. How does the acidification occurs? This is possible if metal ions, the cations, accumulate in the pit or else in the metastable pit. Or occluded cells. I hope you understand now. See here you are not forming external crevice, we are the crevice itself is formed by the corrosion process. Now in order that the metal to dissolve continuously, that pit, the occluded location has to be acidified and should maintain that acidity. Now how is it possible? The acidity is possible is first of all created by the dissolution by the hydrolysis of the metal ions. Look at this, the metal ions will interact with water, hydrolyze and form metal hydroxide plus acid H plus, and H plus in turn will attract more chlorides and form this ones. Assume that these metal ions can easily migrate outside. I form a pit, you have metal ions, they just go out of the surface, what will happen? Here is the metal ion that is coming here, okay. Metal ions are formed here, right. Assume that these metal ions do not get accumulated, they just go away from the surface, get into the electrolyte. So what will happen? Increase or decrease? Decrease. Why will it decrease? No, you are right, pitting will not occur. Why it is not happening? No, what does the metal ions first of all do? If they stay here, what do? They form ions, right? They form hydrogen ions, they hydrolyze. If these ions are quickly moving away from the surface, what will happen to acid formation? The acid formation reduces, the chloride ion migration also reduces, and so the pit becomes unstable, okay. So if Mn plus migrate faster, the pit becomes unstable. Or I put other way around, you need, so to say accumulation cations are needed. If they are not accumulated, they are washed away from the surface, no, the pitting will not be stable, that surface becomes again passive. Now let us look at this. I made this a little bit longer, this is the or length of the pit, or is the pit length. Now please look at here, the metal dissolution occurs, the electrons will travel here and they may combine with oxygen and you can form hydroxide. The electrons also can travel here, combine with oxygen here, and it can form hydroxide, whatever it can form. So you have an anode here, and here you are going to have a cathode. I think most of you are engineers now, right? I am going to put a question to you. I want more cations to be here because when you have more cations, it will hydrolyze and form acid. It also can lead to migration of chloride ions into the pit. Now what makes, now look at, there are two processes. One is the dissolution of metal ions giving rise to this. And what is the other process? The other process is the migration of these ions from the pit to the outside the pit. So now you tell me, what are the governing factors that will make the pit stable? Of course, gravity is one thing. Okay, assume that gravity is there. Okay, gravity is going to be everywhere. Now, what are the other factors in terms of pit dimension? Other one,
Depth of the pit.
the length of the pit and the rate of dissolution, right? So the product length of this one and I, the dissolution current, is a parameter used to describe the pit stability. Please look at, they are multiplied. If R is higher, I can have a lower current density. Why? Because diffusion path is longer. If the diffusion path is shorter, then I must have a higher dissolution rate in order to make the pit stable, right? So the pit stability, this is the criteria used, okay, by a great guy called Galvele. So this is one of the important criteria in deciding the whether the pit formed in a metal will happen or not. Okay. So I think I will not get into too much of things beyond this particular point actually. Okay. Only one thing I want to make a mention that I think is important, that probably you like to know, and then we move on to other aspect of that. Now there are various metallic cations, let us say aluminum, iron 2 plus 3 plus whatever, you may have, let us say, chromium. So very interestingly, that each cations, they produce different pH. That is decided by their they are decided by the K value. For example, Al3 plus water, K value, right? A for that will decide what can be the pH. So they may have different values. Those ions use more acid, less acids. Anyway, let's not worry too much. Okay. So the criteria of pitting is so to summarize what we have seen so far. Pitting occurs in passive metals. Film breakdown and localized corrosion causes pitting, right. Now, you have a criteria called metastable pitting, which can occur even below E pit, right, can occur even below the E pit. Pit stability depends on what? Depends on the pit chemistry, right. The pit chemistry is not promoting, is not good enough, then pitting will not occur, right. So, the pit stability depends upon the pit chemistry, and pit chemistry in turn depends on what? Pit chemistry depends upon the diffusion parameters, which means cation accumulation, right. Which is defined by the criteria called R into I. So, please go through this, I mean, okay, and we can discuss this